Linux In-Laws, a podcast on free Libra open source software. Broadcasting from the United Kingdom and Germany.
Welcome to Linux In-Laws, Season 2, Episode 34. Unfortunately, there's no Martin around tonight because Martin, for some strange odd reason, I reckon it's Spice Trade, and yes, that would be a Star Wars reference, came up very last minute. So we have to do without my beloved co-host, but nevertheless, we do have three important guests on the show tonight, and it's all relating to a very big snake. Without giving away too much, why don't you introduce yourself? Let's start with Eric Snow.
Yeah, my name's Eric Snow. I work at Microsoft on the Python performance team, so we've been doing this for a while now. And aside from that, I've been a Python core developer since 2012. Been working in the Python community for longer than that, of course. And I've spent a lot of time working on various things, mostly related to the CPython runtime, like the import system or sub-interpreters, interpreter isolation, a lot of stuff along those lines.
Mark, over to you.
I'm Mark Shannon. I work with Eric at Microsoft. I'm the tech lead of the team. I've been using Python for a long time, like Eric. Started contributing CPython back 2010, 2011, something like that. I've only been a core developer, well, I say only, not as long as Eric anyway, for about 5-6 years, I think.
Mike, over to you.
Yeah, my name is Mike Müller, and I'm a Python trainer. So I'm involved with Python for 25 years, and I'm doing Python training for 20 years. And among teaching general Python, I teach you quite a bit of high-performance computing with Python, so making Python faster. So I have a lot of contact with people that want to run faster Python, and I teach quite a few techniques to do this. And now there are some new techniques on the horizon that I'm eager to teach also.
Okay, I reckon we have about 2 people in the audience due to the fact that they have been brought up in the 70s, 80s, and then took the time travel bus to 2025 who do not know what Python is, as in who missed out on the last 30 plus years. So maybe one of you could kind of give a very short overview of what this programming language is all about that is driving major workloads, as in about 70% of the matrix servers on the planet, major portions of the Bloomberg ecosystem, as in the financial news provider, just to name 2 examples of significant Python ecosystems. Who wants to go first?
Well, I'll go. So I don't know. To me, Python is a programming language Guido van Rossum created to meet a need. It's like why any programming language is created. He didn't like what was available, so he made one. And a classic. He had some time on a weekend and he hacked it all up, and then it turned out all right. But Guido's background is all in programming languages that are programmer focused. They're friendly to users. They're easy to use. They're easy to learn. But Python's also still very powerful, mostly because it provides a capability to write extension modules in other languages that allow you to incorporate capabilities from other runtimes and libraries on the system that aren't available in Python. So it made a whole ecosystem available, and then it's just developed from there. But it's really been driven a lot by this really innate sense of language design that Guido has that's pretty unique. So it's become a language that's very easy to use, easy to learn, very powerful. It works to glue things together from across all over, which has made it really successful in a lot of different areas, including like machine learning right now. It's really big there because it's able to kind of orchestrate all this stuff going on GPUs and pipelines and all these different things.
Anybody else wants to chime in?
Yeah, Python is the second best language for everything. So that kind of expresses that it can be used for pretty much anything, and you will find Python in all areas, microcontrollers and big machines and web services and automation, DevOps, anything. And I think one reason is because the learning curve is nice. So you need only a pretty small fraction of Python to get something done. But if you want to go deeper and do something more complicated, there's plenty of stuff you can put on later or learn later. So that's one big thing. So Python's very approachable to get started, but you can scale at the other end also.
I couldn't have put it better. A couple of more traits of the language. Full disclosure, I've been using Python for the last 35 years, starting in the early 90s. Major portions of the automation workflow behind the podcast is actually written in Python. And I've really come to love Python for a number of reasons, let's put it this way. A, it's a scripting language, so it does support a REPL, as in you simply can enter a couple of snippets of code and off you go. It does have a strong typing system, which is not enforced at the compile time because Python doesn't have a compiler, although with recent Python versions you have. And of course, the coredevs will correct me in a second. You do have something that is closed to a just-in-time compiler, but we will go into the details in a second. But the beauty is, as the people already pointed out, it's easy to learn, and I'm almost tempted to say it's and the word has been the phrase has been mentioned already. It's a glue language. So because of the massive ecosystem. And the Python package index, as in PyPy, is the best example for this. For me, writing Python code is essentially taking a look at PyPy and GitHub, of course, and seeing what is already out there, and then incorporating these modules into my code base and only writing the glue code. Now, with Python does come a very important reference implementation, and that's actually the subject of tonight's discussion, as in CPython. There are other interpreters are available, but given the fact that we have now two core devs and a very avid user of Python on the podcast, why don't you explain what CPython is and why it's so important and what other alternatives are out there?
Shall I take this?
Go for it.
Okay, so CPython, as you said, is the reference implementation. It's called CPython because it's written almost entirely in C, although the actual library that comes with it is written, a lot of that is in Python. In fact, the majority is in Python. But the core virtual machine, the bit that actually runs Python, is all written in C. It is the dominant implementation by far. All the others are sort of like rounding errors almost. So it's kind of not really maintained as much now, an alternative called PyPy, which was an interesting implementation. It was written itself in Python and then used meta-programming techniques to generate a fast interpreter and JIT compiler. And I guess the only other viable Python alternative is the one, the Truffle Python for the JVM. That's arguably more an experimental thing than a sort of particularly usable Python. That has some interesting performance characteristics. It can be very fast, but uses a lot of memory.
Although other alternatives like Python are available, Python is actually a transpiler that takes a Python code and translates that into C. But the trouble with all these kind of, I'm almost tempted to say fringe projects, they are probably not as close to the standard that CPython sets, because every PEP, and PEP of course standing for Python Enhancement Proposal, as in the infrastructure or the mechanism / process that is used to enhance the language, as is first and foremost implemented in the reference implementation. This is the reason why all of these other environments, for want of a better expression, have a certain lag behind the actual standard. And we're recording this in February 2025, and the actual CPython implementation that is out there, as in terms of version, is 13, help me out here, 13.2 or something like that?
13.2.
Okay.
Yeah, just came out a few days ago, 13.2. 13.2,
exactly. So why don't we, before we discuss the greater Python ecosystem and I'm almost tempted to say tectonic shifts that have been taking place for the last couple of Python versions in terms of 3 releases, why don't we go into a little bit of the architecture of CPython? You already touched upon a C core and the standard library being written in Python, but how it's actually done if you kind of author a script and put it in front of the Python interpreter. What happens then?
Python is generally regarded as an interpreted language, but almost all interpreters you'll ever actually use in practice tend to have aspects of compilers built in anyway. So what will happen to your source code is it will be parsed and then converted into what's called bytecode. And that bytecode is what runs internally on the Python VM. Traditionally, it's just been interpreted, but there is an experimental JIT now, and they'll be moving forwards with that. So potentially there's a level of sort of translations that go on. So you start with your source code, that will be converted into bytecode, and then we'll start interpreting that at runtime, and then potentially that can be converted to machine code. So it's ultimately with sort of a compiler and sort of an interpreter. Traditionally, it was just an interpreter, but we're trying to make things faster, and that's a sort of a part of it.
I mean, that has always been the major issue when people discuss various programming languages, right? That Python wasn't the fastest one.
No, I mean, it's slow for 2 reasons, I guess. One is it's a very dynamic language, not just types, also there's many ways of modifying and introspecting almost all of the objects in the language. So that slows things down, but also just the implementation was always designed to be sort of reasonably straightforward and easy to maintain. I mean, JavaScript is a very dynamic language as well. And, the big investments from Google and others on the JavaScript engines have shown that you can make JavaScript fast. So it being dynamic isn't necessarily an impediment to it running fast. It just makes it harder to do so.
I mean, what I really liked about Python, and that goes back to the day when I started to learn Python, was actually the meta-object protocol, i.e. you could intercept certain features of classes. And for those of the people who are not familiar with object-oriented programming, essentially a class is a template where you can instantiate objects from, which do then do the necessary computational workload, so to speak. And the meta-object protocol, and links, of course, will be in the show notes, essentially are a way to intercept method invocations that these classes define. And Python has a very flexible meta-object protocol that allows you to essentially tweak your way around digital functionality. And this is basically what full disclosure, I did a PhD on meta-object protocols. Again, just with the show notes, he said in vain. Jokes aside, the thing is that attracted me to Python in the first place, but Python has come a long ways ever since. But it's still a very powerful programming language, bar the fact that it doesn't enforce typing. In contrast to, say, Rust, Golang, and probably I'm almost tempted to say C++, never mind Java.
Yeah, that's right. I mean, a lot of the statically typed programming languages allow the compiler to use that type information for various purposes. And, it gives you some measure when you're working on your project of ensuring that you have consistent usage of objects throughout your program. I mean, Python, you can get that through tools that operate outside of runtime, or perhaps, optionally during runtime, but that's not part of CPython itself.
But as of recent versions, type hints in terms of hints that are only interpreted by IDEs, as in integrated development environments, have found their way into Python. Typing is not enforced in Python, but you just mentioned statically typed languages, and statically typed languages do have the advantage, actually most of them would be compiler based. So the compiler would have the chance to enforce typing at compile time and would then be able to generate optimized code for typing. Of course, that is not the case with Python, although, as I said, type hints have been creeping or even finding, for want of a more positive expression, their way into the language, but mostly used for IDEs. Do you think that eventually Python will become a language that enforces typing in terms of you won't be able to code without types? Because at the moment, you don't have to specify types at all. Python does its best, as in CPython does its best, to derive the type, and if it fails, it gives you an exception as an error, or an error generally, and it aborts the program. But given the fact, or given the advantages that statically typed languages do have, do you think ultimately Python will go that way down too as well?
So I have some thoughts about this, mostly that a lot of programming languages require that the programmer accommodate the tools. So do a lot of the work to make sure that the tools can do what the tools want to do. So, I mean, I've worked in various programming languages, and Python is one of the few where very little of the time am I doing anything to accommodate Python. Whereas other programming languages, like with Go, I would spend maybe half my time trying to conform to what the compiler wanted. And so in that regard, that's one of the reasons why Python is one of the most productive languages for programmers, is because it gets out of your way for the most part. Now, type hints and static typing and that category of programming language features is something that is a lot, in my mind, it's very much something that is there to help the tools rather than to help the programmer so much. It can be helpful for somebody coming into a code base to understand the types and everything. And that's useful, but as far as the runtime goes, it's not necessarily so important. And what's one reason why I can demonstrate that is because with the performance work that we've been doing, and Mark can speak more to this, we don't really worry about the type hints, the information that we get at runtime, keeping track of how things are used and what object shapes have and so forth. That's stuff that we can get to an extent more efficiently than the type hints can provide anyway. So it's not really something Python needs. It's, in my mind, more for the benefit of the tools, which is kind of a little bit anti-Pythonic.
Mark, your take on this?
Yeah, so I think it's a bit of a myth that the types and static compilation yield speed. So Haskell is an example of a extremely strongly statically typed language. Yet there are performance. LuaJIT, the fast implementation of Lua, a dynamic language, can outperform and typically does outperform Haskell. Java is almost always dynamically compiled. That performs well, although that is statically typed. So there's no sort of clear distinctions there. As Eric said, for something that isn't statically typed, generally the statistical information you get at runtime will be to any type hints, partly because the type hints can't be trusted. So not only are they not 100% guaranteed to be accurate, but they're also not necessarily the type information you want. So, for example, a type hint might merely say that an object is of a class that has a certain method. But for performance, we want to know exactly what class it is. Or we might want to, the information that the type system is there to provide ease of use, some sort of combination of ease of use for the user and correctness. Whereas the type systems we want are designed around performance. If you're writing C or Fortran, those type systems align. Those type systems are designed for the hardware. But for a more sophisticated language, like the type system is in Python or something like one of these sort of statically typed but expressive languages like Haskell, the type systems often don't necessarily align with what you want for performance.
I know quite a few Rust people that would tend to disagree. Playing the devil's advocate now.
Rust is a very machine-oriented type system. It has structures on top of that, but fundamentally, it's all really describing the layout of objects for the machine.
I mean, the steep learning curve from Rust, and full disclosure, yes, some people consider Linux In-Laws to be a Rust marketing podcast. Martin, if you're listening, this was just for you, right? Anyway, it doesn't matter. Okay, joke aside, no, the learning curve in languages like Rust comes from the fact that the compiler is really enforcing the type system. And yes, it will take you by the hand and it will give you guidance in terms, for example, in terms of type inference, where you don't have to specify types all of the time because the compiler is actually able to infer the types if the remaining if the remaining program code rather is correct. But at the same time, it doesn't provide, for example, garbage collection, which programming languages like Golang and, of course, Python do provide. So it introduces all sorts of, I'm almost tempted to say, complex mechanisms like the borrowing checker, like ownership and all the rest of it to get around this. But Python had garbage collection built into the implementation since day one, if I'm not completely mistaken. Yeah. And maybe you care to comment on the recent improvements of garbage collection in CPython, because that apparently has come a long way.
So, yeah, it's ongoing work, but we now have okay, so first of all, let's step back and describe roughly how garbage collection in Python works. So it's reference counted, which means any object which isn't part of a cycle will be immediately reclaimed as soon as there are no longer any references to it. But the problem with reference counting is it can't collect cycles, because if you have two objects that refer to each other, each has one reference to the other, they always have a reference count of 1, even though they're just garbage. So we need a backup cycle collector.
And the cycle is essentially a circle where two objects reference each other, or they get that wrong.
Yeah, no, that's exactly it. Any number of objects, but the simplest one is just two objects, each have a reference to the other. And those reference counting will just leave them with a reference count of 1, potentially forever. So we need a backup cycle collector. So we've made improvements in both of these. Reference counting we can generally reduce by doing things like when you call a function, we pass the reference from the caller to the callee so that we have less sort of busy work doing reference counts around incrementing it and then decrementing and incrementing ref count. So we're trying to do less of that. And then we've also made improvements in the cycle collector. It's now incremental, although it's not noticeably that much faster. It is a bit faster, but that's ongoing work. So we hope that as we can reduce the number of reference count operations, we can do some major changes in the cycle collector because of the nature of the proportion of cycles versus non-cycles. But that's all a bit sort of future work, to be honest. I think the significant change we've made is that it's incremental and people may notice smaller pauses due to GC, but it's not a big change, to be honest.
Speaking of performance improvements, maybe now's the time to go into the major leaps between version 3.10, 3.11, 3.12, and needless to say, the latest addition to the family, 3.13. Just to throw a couple of bones here, what's it called? Type classes, and it's not abstract interpreters, it's derived interpreters or something like that, basically, where you almost are inching towards a time compiler. But I've just read the PEP, so we do have the expert past. Max yourself out, please.
So the big change 3.10 to 3.11, which was the biggest speed up we've had, was due to the what's called the specializing adaptive interpreter, or even I can't remember, or it's the adaptive specializing interpreter. I think it's the first.
Something along these lines, yes.
Yeah. So once upon a time, back in the early days of computing, a thing called self-modifying code was quite common because people had very limited resources in their computers. So code that sort of modified itself and adapted to run the program faster was quite common. Obviously, actually modifying machine code at runtime is now considered a terrible idea for security reasons, as it probably should be. But with an interpreter, you're really just changing data because the program, the interpreter itself, is running another program which is just data. So modifying that program as you go along is safe. So that's what we do. So basically, we rely on what's a thing called type stability, which is the idea that if a piece of code sees certain types of data one time, the next time it's going to see the same things generally over and over again. Like you may have like the code A plus B in different places in your program, and sometimes it might be doing string manipulation, and other times it's doing integer arithmetic. But in one place, it's almost always doing strings because there's a function that deals with strings, and in another place it's doing integer arithmetic. But they both look the same for the source code. It's only in the context of the function that they're in that they differ. So what we do is we adaptively specialize those different places in the bytecode to, in one case, deal with strings and the other integers. And we have many of these different specializations. I think it's about 100, maybe fewer. Well, obviously, and we potentially will be adding more as we add the JIT compiler because that works at another level and allows us to do more of these specializations. But the main specialization in improvement in 3.11 was the specializations in the interpreter. And I think that gave us it depends on the benchmark and your program and so on. But we've seen softwares like double in speed, but other times it's only take 20% speed up.
I mean, some of the benchmarks I've seen speak about almost up to 50% speed improvement. That's a lot.
Yeah, I mean, it varies a lot. So, like, if you've got a program that's spending all its time waiting on I/O or doing NumPy stuff, you're not going to see much of an improvement at all. If you're like developing a web app where it's mostly pure Python code, there's a good chance you'll see quite a big speed up. Yeah, the 50-60%.
And given the fact that you're moving closer and closer to a just-in-time compiler, what's ahead with regards to the VM that is interpreting the Python bytecode, actually turning the stuff into machine code that can be natively executed? And you already mentioned the security risk here. Any thoughts on the roadmap?
Yeah, so I mean, the security risk particularly is self-modifying code. We're actually sort of trying to design our compiler to not do that. But just to step back a second, people assume that a compiler runs machine code must be faster, but the interpreter itself is obviously written in C and it is running machine code. So it's often the overheads are like the dynamic nature of the language, memory management, and all of these other things. The overhead of like what's called interpretive overhead, the moving the data in and around the interpreter and dispatching to different instructions, isn't necessarily that large a fraction of the runtime, only sort of in the order of like 10 to 12%. So that's kind of an upper limit for what a JIT compiler can speed things up if you just naively translate into machine code. And in fact, if you're too naive translating into machine code, you can make things worse because you just have a lot of machine code, and that isn't very good for the hardware. It causes cache misses and the like. So it's kind of where the JIT compiler is really part of the bit that translates into machine code is really part of what people tend to think of a JIT compiler, which is that it does lots of dynamic optimizations. And what I was saying, exploiting things like the type stability I was talking about earlier. But we're doing some of those in the interpreter anyway, which again reduces the potential advantage of the compiler. So we're not expecting huge speed ups from the JIT. It's not magic, but it does offer us a lot of sort of potential for optimizations that really aren't feasible in the interpreter. So we have a JIT compiler. Its performance is effectively a wash. It's no faster than the interpreter. but it does give us a platform for doing further optimization. So we'd expect it to see, like in 3.14, 3.15, it's starting to show significant speed ups. But just translating to machine code isn't necessarily an advantage. It has to be coupled with other optimizations.
Interesting, because if you're moving to, I don't know, just throwing the bone here, if you're moving this to, say, embedded environments like the IoTs of the world, the Internet of Things of the world, where you essentially do not have a large infrastructure at your disposal, where you actually are forced, more or less, because of, I'm almost tempted to say hardware constraints in terms of CPU cycles, memory, and that sort of thing, never mind some flash memory, because a hard drive isn't exactly available on these tiny devices. And that does present a special challenge, no? And there is an implementation out there called MicroPython, if I'm not completely mistaken, that is exactly aimed at that type of environment.
Yeah, absolutely. If you're looking at embedded, you want to be using MicroPython. CPython is not what you should be using. So, for example, the thing called a BBC microbit, which was handed out to UK school children a few years back, that had 256 kilobytes of flash and only 16 kilobytes of RAM, and they got MicroPython running on that. So you can get it's an amazing effort to actually get Python running on a device that limited, but Damien George managed it. So MicroPython is a pretty impressive piece of engineering, but very different sort of constraints and goals to CPython.
So you don't see going down that road anytime soon with regards to making MicroPython taking on the JIT route enforceably, so to speak, to get things up and running down there at the end of the pipe, so to speak.
No, I mean, it's the other thing is what embedded platforms. I mean, if you consider your phone an embedded platform, I mean that's. It's the old examples of how much, your phone is 1,000 times faster than the Cray one, or sort of olden supercomputers. So, I mean, in terms of phone, CPython, no problem. It's these super low power embedded devices that MicroPython is ideal for. If your device is, run as a power budget of a milliwatt, and weighs a gram or less, then yes, that's the MicroPython is the thing you want to be using.
Yeah. Shameless plug, we do have an episode upcoming in the next couple of months on Kiwi, which is exactly actually an ecosystem that puts Python on your Android mobile phone. But we're going to leave it at that. What we haven't talked about is actually the user's perspective. And given the fact that Mr. Müller is actually in the business of confronting the users of Python, so to speak. Mike, what is your perspective on the recent shenanigans, I'm almost tempted to say, in terms of the recent improvements, to use a much more politically correct word, especially when it comes down to, say, performance improvements, never mind usability, of the last couple of Python versions?
Yeah. So
any thoughts?
So the usability, all the nice error messages are very good, because I teach a lot of beginners, and if you get a strange syntax error kind of thing and people don't know what it is, but now Python says, okay, there's a syntax error, but maybe you forgot this comma or something like this. This is very helpful. So it has nothing to do with performance, but performance of the machine, but the performance of the programmer, because if you find the error faster, you increase your performance quite a bit. But I'm very excited about this free threading directions. I looked at this. So I'm a user of multiprocessing for quite a while. So I just had a small project, I had to generate some videos. So I had to use Matplotlib to generate a lot of plots. And I can saturate all my 8 cores 100%. Everything is running just using multiprocessing. So that's nice. But there's some caveats. So if you don't take care of it, multiprocessing, it tells you, you cannot pick dictionary keys or something like this. So if you make a small mistake on something, you get a very strange error message, which is not very direct, because it's just some follow-up error of something you cannot pickle, or something you did something wrong. You have to be careful. So if you can do this in one process, it would be great, because now my machine has 10 cores. Yeah, the next one in a few years maybe has 100 cores, or not so, because now you can have 100 core processors on the servers already. So in a few years, you might get 100 cores on your laptop. And then if you have 100 cores, you really want to use them, and you want to do as much as in parallel as possible. And the easier this gets, the better for the users, I think, because then if you have all this power available, and of course you need to have the right task for this. So you have something that's kind of independent for long enough, then you can run it in parallel and use your CPUs. And this is something Python makes it very nice. So we have this concurrent future package, which is very simple. So it's just like you map a function, and Python's doing everything for you behind the scenes for the most part. So you don't do much. You just have this function. You have to write the function in the right way that's pickable. Otherwise, it doesn't work. So it has to be serialized to be sent. And there are some constraints to this. I just mentioned sometimes you make a mistake, you get a strange error message. But once you have this one, it's very easy to use many cores from the user perspective. And that can be very exciting for people that they can use a computer. And if you can make your execution 8 times faster, that's not too bad.
It's very interesting observations, Mike. Speaking of concurrent Python, and I'm going back now about 30 years, maybe 25. There has always been, at least in CPython, a so-called global interpreter lock, where the interpreter actually locked a couple of central data structures, and please, Eric, Mark, correct me if I'm talking nonsense now, where the interpreter actually locked a couple of central data structures in order to prevent any concurrency impact on these data structures, especially in a multi-core system. Now, there have been numerous efforts to address this. Subinterpreters probably being the best example, where actually for each and every concurrent Python, there would be a separate process instance being launched with a separate processor, with a separate interpreter, hence the notion to execute your Python code. But as of recent Python versions, and I think it's in 3.13, maybe 3.12, you actually have the option, if you compile Python yourself, to disable the GIL, the global interpreter lock. Maybe some more insights, especially from a multi-processing perspective, where this is going?
Well, that's a great topic. It's something that I've actually been working on for quite a while.
We do have remaining 4 hours, so max yourself out.
Well, so I'll say right now, one thing that I'm working on actually is adding a how-to document on the Python documentation for concurrency. They'll talk about how different concurrency models fit into Python and what characteristics you need to pay attention to when designing a Python program for concurrency, including parallelism. Not everything concurrent is parallel, but and talking about what concurrency models Python supports. So, of course, threads is a really well-known one, goes back decades. But we also have, more recently in Python, we have async in the form of async IO. And we also have had multiprocessing for quite a while.
And async IO is exactly what, for the 2 listeners in the audience who do not know this?
So it's kind of the idea of coroutines, where you have it's a cooperative multitasking, where a function can say, okay, at this point, I'm going to yield up my control of the current thread to some other coroutine, and then you have a loop or scheduler that'll decide which coroutine gets to run next until the next time it yields. So rather than the operating system or the runtime deciding behind the scenes that it's going to stop some function in a thread and hand off control to some other thread. Instead of that, it's the functions themselves get to decide when they're going to hand off control to other coroutines. So that's kind of the idea behind async.
So that sounds pretty cheap to me, because you can stay in userland with regards to, you don't have to create a separate operating system thread, never on process, which will be expensive, depending.
But one of the tricky parts is that with coroutines, at least in Python, but generally, is that they don't run in parallel. So it can be good in situations where you're IO bound and you can yield off control while you're waiting for some resource to finish up. And but otherwise, if it's CPU-bound code, a async stuff isn't really going to help you quite as much. But it's surprising how much of concurrency needs that people have are generally I/O bound rather than CPU bound. So for a lot of people, async programming is a very effective strategy for dealing with concurrency. So yeah, there's these different models. I'm working on a document that provides that, gives examples of how to implement different programs and using these different concurrency models. So one of the ones that I'm including, and something I've been working on for quite a while, is subinterpreters, which is basically, you can think of the Python runtime as a set of state in memory. And the GIL protects that state. So if you have different threads, you don't want data races on that internal runtime state. So only one thread at a time can hold the GIL. And that means that only one thread at a time can be modifying the state. And that way, all the code in the runtime doesn't have to worry about the possibility of data races because only one thread can be touching that state at a time. So the GIL is really advantageous in that regard. The downside, of course, is that for things where you're waiting, but not waiting for I/O, where you're CPU bound, then only one thread at a time can be running, and you run into the problem of you don't really have parallelism for CPU-bound code. So one strategy that I've been working towards is take all that runtime state that's internal to CPython, and it's actually been this way for a while. There's kind of a global state, and then there's this interpreter state. And you can have multiple interpreters or interpreter states at a time, only one active in a thread at a time, but you can have multiple of them in your process. So you can effectively, it's like having multiple Python processes, except all in the same process. Historically, though, that capability was a little limited because they weren't very well isolated, and they still shared the GIL. The GIL was global to the whole process. So one thing I've done is worked hard to get each of those interpreters' states isolated from each other. And then part of that, move the GIL down into each interpreter. So now, if you have multiple threads running and each one is using a different interpreter, they don't share the GIL anymore. And so each interpreter can run in parallel on your multi-core CPU, which kind of solves that problem to an extent. The difference, though, from all the free threading work that's been going on is that with subinterpreters, they're still isolated. So you aren't sharing any objects between them. If you want to communicate between them, you have to essentially pass messages, which is a pretty well studied and understood and somewhat familiar programming model for people. Like you think of Go or some other language. Smalltalk had, to an extent, various other languages, if I remember right, Erlang. And so this model of you have these isolated kind of abstract threads of execution with some form of message passing between them. Now, CPython, we can get more sophisticated than that. But that's a lot of the things I've been working on to kind of resolve the challenge of the GIL, is to support having these multiple isolated interpreters that can take advantage of multi-core parallelism. So that landed in 3.12, but it isn't really exposed to Python code yet. So that's something. I have a PEP 734 is the PEP to introduce a standard library module that exposes subinterpreters to Python code. Right now, it's only in the CAPI. And Python has a robust CAPI, and it's relatively straightforward to write extension modules that can make use of that CAPI, but it's not really, it's still a barrier to entry to the feature. So that's one thing I'm working on. I'm hoping to get that standard library module in 3.14, but we'll see how that goes.
Details, of course, within the show notes. Any thoughts before we close this up? Any thoughts on what's missing and that we didn't discuss on the road to world domination for Python?
I can think of one thing is that, and there are ongoing efforts in this regard. There are kind of two places where Python historically hasn't had quite as much of an impact or a reach. And that's one is in the browser, and the other is in mobile devices. So both of those, there are ongoing efforts to kind of sort that out. With the advent of WebAssembly, it provides an opportunity to put Python running in your browser, which is pretty neat. So that's something that people have been working on for the last couple of years, and then there's great projects like Beware that support writing applications for mobile devices in Python. So those are kind of the two places where Python really has room to expand a lot. So neat stuff.
Mark, any thoughts from your side, or Mike for that matter, on this?
Yeah, I would second the WebAssembly thing. So it's a very interesting project. And actually, there's also a place where MicroPython comes into play again, amazingly, because you can use Python, which is a full-blown CPython compilation to WebAssembly. But it's a little bit big, so the loading time is a bit long. But you can have a second version. You can have MicroPython. If you just want to do something simple, MicroPython might be good enough. And then you loads much faster because only a few kilobytes in size. So that's very interesting. So if you just want to write something simple in that's going on in your browser, the MicroPython is going to do it. If you really want to load NumPy and SciPy and everything in the browser, then you need to use Pyodide, but then you have users that have time to wait for this. So that's very exciting. So you can do pretty much everything in the browser that you can do on the desktop once you have those things compiled, and quite a few extension modules in Python now are compiled to or compilable to WebAssembly.
The only thing I have to say is Python traditionally has been this glue language, and I think the things it's gluing together are changing. So Rust obviously is making a big impact. So I can see a future where it might still be CPython, but a lot of stuff in CPython and a lot of the extensions will be Rust. I don't know how that will actually change things. Hopefully it'll just make things more reliable, but that'll be interesting to see.
Interesting perspective there, Mark, because I concur actually, because I slowly see for want of a better expression, the invasion of Rust into the Python ecosystem right now as we speak. Whether that's a good or bad thing remains to be seen. The Linux kernel has made great strides with regards to putting the infrastructure in place to enable Rust code to the kernel. But as of late, there have been, I think, one or two naysayers, details maybe in the show notes, that say, no, sorry, we're going to stick to C and that's the end of it. Funny enough, Linus wasn't one of these people. So the jury is still out there of what's going to happen in the kernel with regards to Rust. But I clearly see the writing on the wall with regards to Rust approaching frameworks such as NumPy, Pandas, and all the rest of them that have been traditionally augmented with C rather than just kind of native Python for better speed and, needless to say, also attack surface, never mind safety.
Yeah, Rust brings a lot of great tools to Python. If you use Ruf or UV or Pixie or all those new tools, Polars, libraries. So Rust is not a competitor to Python in any way, I would say. It's just one of the languages that replaces the C extension or some other language they use for writing it and makes Python faster. The tools that you use in Python, so for the Python programmer, it doesn't really matter. In the end, things are faster.
Indeed, and with that, we've come to the end of this very interesting episode. So it's time for the POXs. Eric, what's your POX?
I've actually, I don't know, totally unrelated, started getting a little bit of snorkeling. I live in Utah, which is in winter right now and cold, so not a lot of opportunities where I live, but there are plenty of neat places. Just kind of a neat activity, snorkeling. Get out, not really a lot of equipment or training needed, and you get to go see some beautiful places, get a perspective on the underwater world that you don't get when you're up on the surface.
Okay, interesting. Any particular details you can share, or is it just kind of the stuff in general?
Well, I'm pretty new to it, but it's kind of a neat thing. It doesn't require a lot of equipment or anything, so it's really accessible, but a neat experience, especially if you live close to the ocean.
Mark, over to you.
Okay, slightly different tack. The film Nosferatu, the 2024 version, not the original 1922 version. It's pretty visually impressive film, and it sort of harks back to sort of the original sort of vampire thing, not as sort of teenage romance sort of stuff. So I'd strongly recommend that as a film.
I read about this, and quite a few people actually did recommend this to me, but apparently it can't touch the original, as in going back to 1928 or whatever it was. But I've yet to see this, but I'm really looking forward to it. And Mark, thanks for mentioning it. Mike, over to you.
Usually when you watch a movie, you sit, and people say now sitting is the new smoking. And people recommend to stand, but standing might not do it. You should need to walk. But the problem is you still sit many hours during the day. But there are some things called the soleus push-ups. So soleus is a muscle at your calf, the one below. And it's a very special muscle because it has a very different metabolism. So I have to explain a little bit, otherwise it doesn't make sense. So it uses the energy very differently. It can use the glucose from your blood directly, where the other muscles use glycogen, which is the form that's stored in the muscle itself. So this small muscle is very different because it can use up quite a bit of your glycogen. And that's the problem if you eat and sit, then you don't move, and that's can have health implications. That's people recommend that you move all the time. But now when you sit and you just do some kind of sitting calf raises, which is called the soleus push-up, then amazingly scientists, there's a new scientific study about it, or several studies, actually they did a very sophisticated study. They found out that you can halve your blood sugar, which is the problem that you have when you sit, quite a bit. So it's like you do a slow walk while sitting, so to speak. And the nice thing, this muscle doesn't tire. All other muscles, when you use them, after a while, they fatigue. But this muscle doesn't fatigue. So they had 80-year-old ladies that did this for hours on end, and their muscles don't tire. They can do it. So there's no age limit on it. And you can do it whenever you sit at a desk or something. And it looks a bit silly maybe, but you can raise your calves and like in a frequency like 50 to 100 a minute. So there's a cadence. So 50 to 100 hertz. And this is like you do a slow walk. So if you sit there for a few hours and you do a slow walk while sitting, in terms of your metabolism, maybe it's not a bad idea. So it's something you can do when you watch your video. Just sit there. You have to get into the habit to raise your calves, and it's like you're walking while you watch your video.
That sounds amazing, because actually if you do this in the workplace, you can do this without going outside, and skiving is in terms of skiving work and taking a walk, right? So impressive.
Yeah. So I can send you a link if you like, because
yes,
there's a 1 hour explanation of the scientists who did it, and I just tried to cut it down in 1 minute. So I cannot really do it justice, because they did a very sophisticated study and then muscle biopsy and then measured and stuff and all kind of things. But it's kind of just it's if you sit there and just raise your calves with this muscle, which is very special, then you have the same effect in walking slowly.
No, that's greatly appreciated. Please do send me that link so I can include in the show notes, because I reckon quite a few, maybe 3 or 4, if not 3,000 or 4,000 listeners of our podcast will be exactly looking for this. No, seriously. I mean, I reckon the majority of the people out there listening basically are bound to office jobs and don't get out that much between 9 and 5, I'm tempted to say. So that would be an ideal complement to their daily, I'm tempted to say. So, of course, links are greatly appreciated. Okay, and with that, it's up to MyPox. MyPox is actually another franchise of the Star Wars universe. It's called Boba Fett. It's actually a mini-series of 7 episodes. I won't give away too much, but it deals actually with the Boba Fett character of the preceding episodes, and all your favorite characters do make an appearance, including Ashoka, Grogu, and of course the Mandalorian. It's only 7 episodes rather long, so it's not that much. And of course, details will be in the show notes. So if you are a subscribed fan to the Star Wars to the Star Wars franchise, you don't want to miss out on that. And with that, Eric, Mark, and Mike, thank you very much for being on the show, and looking forward to having you back in a future episode to give a status update.
Yeah, thanks for having us.
Thanks for having us.
Thank you. Take care. This is the Linux In-Laws.
You come for the knowledge,
but stay for the madness.
Thank you for listening.
We hope you like this feature presentation. If so, please spread the word. If not, please let us know. Feedback at linuxinlaws.eu.